Welcome to Furnaces North America 2020, the virtual conference. This is Dan Herring, the heat treat doctor, president of the Herring Group. The Herring Group was established in 1995 to help members of the thermal processing industry in the areas of heat treating and metallurgy. We have had a long and close association with the Metal Treating Institute and all of its members. And this presentation continues that work. Today we are going to talk about equipment maintenance, and in particular how preventative maintenance will increase your profit margins. It is important for us to realize that heat treating equipment comes in all shapes and sizes. Here are some examples of typical atmosphere furnace equipment. Most everyone is familiar with these basic designs. We have box furnaces, pit-style furnaces, mechanized box furnaces, also called integral quench or sealed quench furnaces. We have mesh belt conveyor furnaces, whether those belts are alloy or ceramic. We have rotary hearth furnaces and pusher style furnaces. All of these units have different maintenance needs and maintenance demands. Still more atmosphere furnace equipment is illustrated on this slide, including bell furnaces, car bottom furnaces, roller hearth furnaces, rotary drum furnaces, box furnaces with retorts, and cast link belt furnaces. In addition to atmosphere furnace technology, we also have applied energy technology. The most common example is induction heating equipment, which, like its atmosphere counterparts, comes in a variety of shapes and sizes for a number of different applications. Bar heating is an example, scanning another, brazing and melting, for example, in a variety of horizontal or vertical configurations. Again, each demanding its own individualized maintenance and maintenance plans. In addition to induction hardening, there are other examples of applied energy in the form of, for example, flame hardening equipment, and also brazing equipment, torch brazing being a good example. In addition, in most, if not all, heat treat shops, you will find some type of oven, whether it be in a batch configuration or a continuous configuration, such as the monorail conveyor oven illustrated. In addition, we will see ancillary equipment. Shown here is an example of a gas generator, but we will also see washers, temper units, shot peening and shot blasting equipment, cryogenic equipment, and the like. Finally, many shops have vacuum furnace equipment in them. Vacuum furnaces typically come in several configurations, one of which is a horizontal design used for processes such as sintering, annealing, hardening, brazing, and running very special or customized processes. Vacuum equipment has its own demands on maintenance, as we will see. Another common style of vacuum equipment are vertical vacuum furnaces, which are typically called bottom loading equipment. These vertical furnaces can be equipped with either a gas or high pressure gas quench or an oil quench. In addition to horizontal vacuum furnaces consisting of a single chamber, there are many dual and multi-chamber vacuum furnaces as well. And these furnaces can be equipped with either an oil quench or a gas quench, or in some cases, both. Vacuum furnace systems for low pressure vacuum carburizing and hardening are becoming ever more popular. Again, these systems can be designed with oil or gas quenching, or both, and often consist of multiple chambers or modules or cells, each requiring perhaps a different style of maintenance. Now that we've had a look at the various types of heat treating equipment that might be found in a typical shop, it's important to look at what we call the model of material science. I look at it as a series of overlapping rings or links of a chain. As we all know, a chain is only as strong as its weakest link. So performance, material selection and properties, microstructure, process, and equipment are all intimately linked together. In addition, the customer, the engineer, the metallurgist, the heat treat operator, and yes, the maintenance personnel are all intimately linked together. If one of them fails, they all fail. If a customer demands performance expectations beyond our capabilities, the chain will fail. If we use the wrong process recipe, the chain will fail. If we poorly maintain our equipment, the chain will fail. If the engineer selects the wrong material or the wrong properties, the chain will fail. In the good old days, we used a discovery or empirical-based methodology. We started with a piece of equipment, figured out a process to run in that equipment, developed a microstructure as a result of that process, figured out what mechanical properties or other types of properties we had, and we defined to the customer the performance he could expect. Well, the good old days are certainly old, but not necessarily good. Today, we are a science or engineering-based methodology where the product performance is king. The product performance dictates the choice of materials and the type of properties that are necessary, the microstructure that needs to be created, the process to achieve that microstructure, and often dictates to us the best or the optimum piece of equipment to run that process in. So not only is performance, properties, microstructure, process, and equipment linked together, but customers, engineers, metallurgists, heat treat operators, and maintenance personnel are intimately linked together. And of course, overviewing everything is quality and the quality department. Now, why is this important to maintenance? Let's talk about that. Based on my many years in the industry, I have seen two distinct styles of maintenance practices emerge. That is, planned preventative maintenance programs, where we plan the activity, we execute the activity, then we go back and evaluate the activity, and finally revise our plan, what I typically refer to as a peer review, or the repair as needed strategies. In other words, we'll fix it when it breaks. I wish I could sit here and say that one of these two methods was superior to the other. In truth, I cannot. What I can say, however, is that while neither has been proven to have a distinct cost advantage over the other, the planned preventative maintenance programs much better match the production demands of manufacturing and ultimately have a better impact on our profitability. The if it breaks, fix it philosophy leads to loss of profitability. So what's involved in a planned preventative maintenance program? Well, first of all, we have to monitor the component usage. And this is typically done via hour meters or an understanding of how many cycles a particular component or piece of equipment has run, how many loads the furnace has run in any given time period. Also, it involves identifying essential spare parts. As heat treaters, let's face it, we would always like to have a spare furnace or two in inventory. We can't afford that luxury. So we have to determine what are the long lead items and critical spares and have those in inventory. Also, it is important to do detailed record keeping. And if I had one criticism of the maintenance department, it's not in the work effort. It's in record keeping. And oftentimes, maintenance needs help because one of the requirements during a repair is to determine the root cause of the failure. And remember, there can only really be one root cause. And secondly, we have to have an explanation of the repair. Why it was done, what was done, where it was done, when it was done, and how it was done. Candidly, too often I look at maintenance logs and they will say things like, change the thermocouple, or replace the fan belt. Well, why did that fan belt require replacement? What caused that thermocouple to go bad? These are parts of good record keeping. And certainly, ultimately, out of this investigative process, our goal is to establish the mean time between failure. So let's look at the steps that are involved in a good planned preventative maintenance program. The first is understanding any external constraints that are imposed on the maintenance department with respect to such issues as equipment usage and, yes, budget. We don't often have an infinite budget to do the work that's necessary. There are compromises that need to be made. How often do you find that maintenance is given 2 weeks to repair a unit, only to discover that production wants it back in 3 days? It's ironic how many times I've been involved in that very scenario. So going into any maintenance program, we have to understand how long we can have that equipment for and what is our budget. Second, we must understand how the equipment is being serviced. In other words, how should it operate and how is it working now? How it's working now is perhaps not how it should be working. But if we don't understand how it worked when it was brand new, it's hard to understand if it's working properly after years of reliable service. And third, we need to tailor our maintenance plan to what I call realistic expectations. Again, have these critical spare parts in stock and understand which spare parts must come from the original equipment manufacturer and which spare parts can be purchased from a third-party supplier. And from those third-party suppliers, are we getting parts of equivalent or better performance? Sometimes the third-party suppliers outperform the original manufacturers. Other times, the original equipment manufacturer's parts are specifically engineered for the furnace that we're dealing with. So we have to understand that and plan for it. In addition, we must divide the furnace into sections or areas and sometimes divide our work effort into small groups or smaller areas serviced by specific disciplines. I can't tell you how many times I've seen an electrician try to do a mechanical maintenance function, or vice versa. We have to focus on those components or assemblies, either internally or externally, that are critical to the functionality of the equipment. And we have to understand both how the equipment operates from an external view and, with all appropriate safety precautions taken, from an internal point of view. In other words, we need to observe how the component parts that make up the furnace systems interact with one another. I recall vividly a client taking and rebricking an inner door on an integral quench furnace. And he discovered that as opposed to laying the brick vertically, he laid it horizontally and improved the life of the inner door because he understood the movement of that door. And then, of course, as we've talked about, we need to put the repair information into a usable form, and in this day and age, a retrievable form. Given a retrievable and searchable form, given the advent of computers and the access we all have to computers today, this is critical. But in addition, we need to review the maintenance and repair work with management so they have an understanding on what we've done, what we've assumed, and what we believe may or may not happen. In addition, we have to get together as a group, not only the maintenance department, but the maintenance department, the operators, the supervisors, someone from quality, and someone from management. So we have a feedback on those repairs. And we need, therefore, to revise our preventative or our planned preventative maintenance program accordingly. Other aspects of a good planned preventative maintenance program, including establishing a mean time between failure for key components. We want to conduct a cause and effect analysis, and we want to determine the root cause of a failure and don't just fix the obvious problem in front of us. We want to be disciplined. We want to realize the benefits that a very well thought out, structured program that's rigidly adhered to will have. And for all the maintenance personnel listening out there, this is not a punishment, but rather prevention. And lastly, as our parents taught us, do the job right or don't do the job at all. If you don't have the right tools, if you don't have the supplies on hand you need, it will be difficult, if not impossible, to succeed. I cannot tell you how often I've seen a temporary patch or a temporary repair continue forever without being revisited until it catastrophically fails. So again, do the job right, and the planned preventative maintenance program will succeed beyond your wildest expectations. Now, planned preventative maintenance programs are not easy. And in this presentation, I've given you an overview of what's needed, but I can tell you that they will increase your bottom line profitability better than any other type of maintenance program. So finally, we've come to the end of the presentation. But I cannot emphasize enough how important it is that during the actual repairs, you have the help you need, both internally within the company and externally from the original equipment manufacturers, the suppliers, and yes, at times from consultants, to make your maintenance programs and plans a success. Because your profitability is ultimately the profitability of the industry we all love and serve. Happy maintaining, everyone. This is Dan Herring, the Heat Treat Doctor.